We had mentioned Redfield ratio before. Basically, it's the nearly constant ratio of carbon, nitrogen, and phosphorus, as well as iron in various different species of phytoplankton. Here is the table showing the actual numbers. Remember, Redfield was the scientist who discovered it in the 1960s. And we mentioned how even the water tends to have similar ratios as the living species, and the question was chicken and egg, which came first, right? The recycling idea means that the animals, the phytoplanktons, are assimilating the nutrients, and then they are being disintegrated, decaying, dying, and remineralizing. So there is a cycle over time. Together they probably decided this ratio that remains nearly constant. I say nearly constant because I'll show that there are places where it does vary. Then the question is, why does it vary? It gets into very detailed biological, biodiversity, and other issues that we will not get into. But just to touch again on this in the context of carbon cycle, relative number of atoms in living phytoplankton, carbon, nitrogen, phosphorus, and iron has been added here. 106 to 16 to 1 to 0.01. So iron is a micronutrient that is needed in small amounts, but it is a critical nutrient, as we said, in the Eastern Pacific and Southern Ocean, where there is a lot of nitrate. Why? Because there is upwelling. All the nitrate doesn't get consumed. They're called high nitrate, low chlorophyll, or HNLC region, because there is not enough iron to use up all the nitrogen, because iron is limiting. So what you need to remember is Redfield ratio typically is C to N to P, but iron has been added here. 106 to 16 to 1 is mostly what we use, but iron is also something to remember. The mean N to P ratio in particulate organic matter in the Mediterranean Ocean is shown here. You can see that the ratio of 106 to 16 is obviously being violated in many places. Okay, this has all sorts of consequences because of fertilizers and other things. Coastal runoff from the rivers, etc., also comes with a different N to P ratio. 16 to 1, remember, 106 to 16 to 1. The species, size classes of species, remember diatoms, Prochlorococcus, Synechococcus, picoplankton, nanoplankton, there are different sizes involved. The ratio changes if you change the N to P ratio, but here there are various reasons of how phosphorus is used and so on, that the Redfield ratio decreases towards the expected value of 16 as you come towards the entrance to the Atlantic Ocean. So the point is that the Redfield ratio is not always constant, but when it deviates from the standard, then you have to understand why it deviates in that particular region. Just to look at again the seasonal cycle of the biosphere, we have the high spring productivity in the polar regions. Remember those productivity seasonalities. Nutrient is not limiting here. Light is limiting. So when light comes up, sun comes up in the spring, there is huge blooms. Tropics, light is obviously not a limitation, but nutrients are, because it's strongly stratified waters other than coastal upwelling and equatorial upwelling. The red colors are high productivities, and you can see that the upwelling regions are productive, but not as productive as the coastal regions. Of course, you have to be careful about the colored dissolved organic matter coming in the rivers as well. Nonetheless, these yellow and reddish colors show that these regions are much more productive than here. So nutrient is a critical ingredient for productivity. And even though there is a lot of light here, you can see these are the deserts of the ocean, as we said before, because that's the subtropical gyres where you have convergence, water going down, so nutrients are not available in the euphoric zone. So light is available, but nutrients are not available. So it's just cute to look at it again. To connect back to our understanding of the ocean circulation now, this is looking at deep ocean nitrate and oxygen. We looked at the profiles, but let's look at it in this context as a map. So this is a strange map, but showing the Atlantic Ocean with the mid-ocean ridge, the Indian Ocean, and the Pacific Ocean. Okay, Indian Ocean is here. So let's just focus on the Atlantic and then come into the Pacific. Okay, nitrate. What do you expect? You look at the North Atlantic, it has low values in micromole per kilogram, increase towards the south, and then Southern Ocean brings in here. In the North Pacific, the numbers are the highest, 36 micromoles per kilogram, whereas the oxygen is the other way. It's 260 micromoles per kilogram here, decreasing, and you get the most oxygen depleted waters in the North Pacific. Why? Now you go back to your thermohaline circulation or the global conveyor belt, right? You have deep water formation here, so the surface productivity is not accumulating enough nitrate. There is productivity, recycling, everything fine. The water sinks, it's taking low nitrate waters. Remember, nitrate is low at the surface to the deep waters. Nitrate keeps falling to the bottom waters, keeps accumulating as you go down. Mixes here, makes a few circles around the Southern Ocean. Oldest waters are in the North Pacific because that's the end of the thermohaline circulation. That's where the water has to come up all the way and go back through the Indonesian seas, back around Africa into this region and other deep water formation regions here. So the waters here, obviously there is productivity near the surface, recycling, but falling to the bottom. So there is accumulation for a long time of nitrate at the bottom water in the North Pacific. By the same token, high oxygen waters near the surface are sinking here. So deep waters have high oxygen here. Oxygen keeps getting depleted as you go along, and the most depleted waters are the oldest waters that are found here. We can actually age these waters. We do that by using one of the carbon isotopes that is called C14, has as opposed to C12 and C13, it's C14, which is radioactive, and it is in nearly constant concentration at the surface, but once it goes into the ocean, it begins to decay into other forms of carbon. So the oldest water will have the most depleted C14. So you can go to the bottom of the ocean, take water samples, measure the C14 depletion. Remember, we measured delta O18 depletion to look at glacier volume and so on. Same idea. Oldest waters will have seen the atmosphere the longest time ago, so they would have most depleted C14 that was coming down from the atmosphere. All cute, right? Everything connects. Productivity, nutrient concentrations, thermohaline circulation, old waters, new waters, and